So let's look at a plug flow system. So with a plug flow system, what we can think about this is, remember, we talk about this plug, okay? This packet of material. And if you think of a train, there's some, it's kind of shown here with a CSTR. As this train moves down the track and it moves along, there is no contact between this boxcar and the one behind it or the one behind it. So each boxcar is totally separate. The mass stays in that boxcar and it's just going to move down the tracks. We can describe it this way here, so with a pipe, and we have a plug here. So when we look at this, we will assume that this parcel is moving down the pipe. We will assume that we have no dispersion. We will assume that, okay, here's my parcel. I have no mass entering and I have no mass leaving that parcel. So just think of it as a balloon. If I put a balloon in a pipe and that balloon were to move down the pipe, I would have no mass, assuming the balloon is fully impermeable, I would have no mass moving in and out of that balloon. And that balloon is just going to move down the pipe. It's just going to move, and eventually it leaves the pipe. So essentially what you have is a completely mixed reactor that's moving down this pipe, this duct, this river. Okay, if you took a balloon and you threw it in the red cedar and you pulled it out when it finally got to the confluence of the Grand River. So we're on campus. So here's the MSU campus. Here's the river. Okay, we're going to dump a balloon. Here's our balloon. And it's going to float down the river. And eventually it's going to get to where the red cedar meets the Grand River, and it all becomes the Grand River. Okay, here's my balloon. If that chemical were reactive, did the concentration change? So you threw in a balloon, and inside the balloon is a reactive chemical. You go down to the confluence of the Red Cedar River and the Grand River, and you pick out the balloon. Is the concentration the same? If it's reactive, it will change. The plugs can be reactive or non-reactive. But this, we said it's a reactive pollutant, so it will change. The concentration here at the Grand River is a function of what? It changed with time. And what else? What other term can we think of? Actually, there's two other we can think of. It's related to time. The decay rate. Okay, but let's keep the decay rate constant. Distance, exactly. Velocity. And they're all related. So time, distance, and velocity. So when we look at plug flow reactors, we can look at time, we can look at distance, and if we're looking at distance, we'll typically look at velocity, okay? Because all those terms are related. Now, eventually, it gets out to Lake Michigan. The mass inside, so the mass in my balloon, that's equal, and write the general equation. Do I have any mass entering my balloon? The ideal, no. So that's 0. Do I have any mass leaving my balloon? So the change in mass with respect to time is equal to the mass reacted, negative, okay? So again, we pull that volume. The volume of my balloon didn't change. dc dt is equal to minus k C, B. So think about my parcel. My parcel doesn't change. Okay? The volume of my parcel, the volume of my balloon doesn't change because I have no mass entering or leaving. So volume cancels. And again, I end up with the same expression, dc dt is equal to minus kc. And if I integrate this from C0 to CT, and from time t 0 to time t, I end up with that same expression, ln c over c naught is equal to minus kt. The next set of slides actually go through this same thing that we just did. So think of this, here's my parcel. The volume of my parcel doesn't change as it moves down the pipe, or my balloon volume of my balloon doesn't change as it moves. So we could think about it as, if we go, here's the Red Cedar. And let's say you decided to kayak from the MSU campus to the Grand River, where it joins the Grand River, and all the way to Lake Michigan, and out into Lake Michigan. And you're going to kayak all the way through. And on your kayak, and I'm not, you are on your kayak, you're carrying a reactor. And you're going to kayak down. And your reactor's closed, so there's no mass entering or leaving. Eventually you get out in Lake Michigan. So you're finally out here with your reactor. It didn't change in volume. So the concentration here is a function of the distance you traveled and the velocity at which you traveled, or the time that it took you to get from here to here. That's what we're describing with a plug flow system. So your control volume is this parcel of fluid. And I think I've probably explained this, hopefully, enough that you can see that this is the equation we'll use for a plug flow system. So now let's go think. Again, we have essentially the same system. So we have, think of it as a pipe, and the solution is entering at 100 milligrams per liter. The volume in this reactor is 500 cubic meters. The flow rate entering is 50 cubic meters per day. So it's leaving at 50 cubic meters per day. And it reacts according to first order kinetics. So we showed that with a CSTR, using these conditions, we would end up with a concentration leaving of 28.6. So what is the concentration leaving the plug? Is it 28.6? Is it greater than? Is it less than? What do you think? So is it 20? Okay, we have one brave soul, 28.6. Anyone else want to redraw? We've got this pipe. The volume is 500 cubic meters. Q is entering at 50 cubic meters per day. Cn is 100 milligrams per liter. K is 0.25 inverse days. Q out is 50 meters cubed per day, and we want to know C out. We have this parcel, so we're looking at this parcel of fluid as it moves down the reactor. So the change in mass with respect to time. So you're thinking about this parcel. We have no mass in is 0. So there's no mass entering this parcel. There's no mass leaving the parcel. And the only change is due to the reaction. So again, we have V dc dt, because the volume of our parcel is unchanged, and that's equal to minus k cv. V cancels, we end up, and I'm just going to skip the step. Okay, so when we integrate, we end up with this expression here. T is our detention time. This is TD, or detention time. Exactly, the parcel acts like a mini batch reactor. That's exactly what it does. So think about the canoe. If you had a mini batch reactor and it was in your canoe, okay, and you simply transported it down the river, that's exactly the situation. So it really is, it acts as a mini batch reactor. And TD is equal to 500 cubic meters divided by 50 cubic meters per day, and that equals 10 days. So C is equal to 100 times e to the minus 0.25 inverse days times 10 days. Make sure your units are consistent. It's less. Okay. It should be less. Thanks for doing that. So let's think back. So one reactor, we had 28.6. Two reactors, we had 19.8, if I remember right. 10 reactors, we had 10 point here with our Plugflow, same volume. So the volume is constant in all of these. The total volume is constant in all of these. We have 8.2. And with a batch, we allowed it to go. If we had done the batch and we had done it for 10 days, we would have come up with the exact same answer. We just allowed the batch reactor to continue for essentially an infinite amount of time. So if you think about it, as we increase the number of our reactors, the system behaves more and more like a Plugflow reactor. So the more reactors we put in series, the closer it approximates the Plugflow reactor. If we had 20, okay, we would approach that 8.2.